Okay, so when two things collide and end up with two new velocities, or one new velocity if it's an inelastic collision, there's going to be a change in momentum that happens. This equation can apply to both of those. Okay. Impulse, when we're looking at a collision impulse, we're looking at a really, really short period of time. Okay, pretty much the exact moment of impact, there's a change in momentum. If we're looking at the impulse or the change in momentum of just a singular object, maybe as it slows or as it changes direction, something like that, it could be longer periods of time. Okay, and typically our problem will give us the change in time. We won't have to necessarily calculate the change in time. For the most part, it'll give us that. So we can find the impulse using this equation listed right there, or we can use a couple different ways to get there. Okay, we know that the momentum equals mass times velocity, but if we want to find change in momentum, we can find mass times change in velocity. From there, we can substitute and connect these two equations into one to help us solve for that change in momentum. Okay, so when we solved for regular momentum, it was just P equals m times v. Now if we want to find the change in momentum, we can just take final minus initial for velocity. So velocity minus v sub o. Okay. So then we can go ahead and connect those two equations. So force times time equals mass times change in velocity. And this will be an equation that we'll use pretty often, okay, in terms of impulse. A question may not even necessarily ask for impulse, but we can use this equation that has to do with the impulse of an object to solve for these things, force or mass or velocity or time. Okay, so it kind of ties everything together in those parts. Okay, so let's go ahead and just try some. What force is needed to bring a 75 kilogram object traveling at 44 meters per second to a stop in 2.1 seconds? Okay, I'll give you a couple minutes to get it written down, and then we'll start walking through what variables we have and what we're looking for. All right, so we can go ahead and start making our list here of what we have. We have our mass, which is 75. Our velocity initial, which is what? 44. What's our velocity final? 0, because it says it comes to a stop. All right, and we know that our time is 2.1 seconds. All right, so we're going to go ahead and solve for a force. So we can take m delta v equals force times delta t. Our mass is 75. Velocity final equals 0. Velocity initial is 44. So on our left side of the equation, I think we get negative 3,300 equals 2.1 F. Okay, so our force should be what? Negative
1,571.
Okay. Newtons. So tell me what it means that our force is negative.
It's like doing against what the weight was.
Yeah, it's opposing the motion, okay? So this object's trying to slow down or trying to move, I guess, and this force is making it slow down. So it's opposing that motion, which is why it's negative. Okay. You can ask for impulse two different ways. You can ask for it by saying what's the impulse, or we can say what's the change in momentum. Okay, so change in momentum is the same thing. We're still solving for delta P. We're given a force and a time, so we'll solve using this equation. $192, what's our units? Yeah, that's fine. We can do that way. We could say kilograms times meters per second, or we could say newtons times seconds. Okay, you could do it either way for momentum. Okay, since we took a force times a time, that will give us newtons times seconds. Remember, kilograms times meters is a newton. So Newton times second will work as well. Okay. (192 newton seconds). Okay. Some of these impulse equations or some of these impulse problems are going to require you to look back into your kinematics equations. Okay, so we get to go back and solve for velocity and acceleration and some of those things we might need to solve these impulse equations. Okay, so this one will require us to solve velocity first. Okay, so what happens is this object is dropped 3 meters, which makes its final distance or final displacement, I guess, 5.4. So we can look at this two different ways. We can say it's fallen, 3 meters, it's landing 3 meters below where it started, or we could have our y initial equal 8.4 and our y final equals 5.4. Okay, you can do it either way when we plug it into our kinematics equation. Okay, so what kinematics equation can we use if we don't have time and we want to solve for final velocity? We can use v squared equals v sub o squared plus 2a delta x, or delta y in this case since it's vertical. All right, what's our initial velocity of a dropped object? 0. Good. Good. All right, so we're going to solve for v final. We know this is 0. What's our acceleration when we deal with falling objects?
Gravity.
Yeah, good. Negative 9.8. And then you can plug this in right here, this section of your t-chart, two different ways. You can plug it in as final minus initial, which is 5.4 minus 8.4. Or you could plug it in as just a negative 3 since it lands 3 meters below where we started. You can do it either way. Okay? So we'll go ahead and solve for our final velocity here. All right, what did we get for our final velocity? 7.67. Is there anything that we're missing here? We're missing something. Okay, in our answer. Is the object going up or down? Down, which means our velocity needs to be negative. Okay, so this is one of those types of problems where we had to go back and recognize that it was going down because our math doesn't show us that it's negative because we had to take the square root. Okay, so we have to make sure that we recognize that it's going down, which means it's going to have to be a negative velocity. Okay, so now we want to find the momentum of the object. Does it ask us for the change in momentum or the impulse or just the momentum? Just the momentum. So we can just use our equation P equals mass times velocity. Okay, because we want to know the momentum at that exact moment, which is why we solved for final velocity during that fall. We wanted to know the velocity at exactly that moment. So P equals 4.3 times negative 7.67. Do we agree? Okay, so what does the negative tell us here? What's the negative momentum mean? Yeah, just that it's going down, okay? It's in the downward direction, that the momentum is going down. Okay, do this one on your own. I know I gave you the answer, but I want you to try and figure it out yourself. Do we agree? Everyone get 4.46? Okay. When we talked about elastic collisions at the very beginning, we said specifically that for elastic collisions, kinetic energy is conserved. That means within this collision, 100% of its kinetic energy should be transferred to the second object when they collide. Okay? There should be no kinetic energy lost during this collision. Okay, this is specific for elastic collisions. In inelastic collisions, kinetic energy is not conserved. Momentum is conserved for both type of collisions. Kinetic energy is not. Okay, it's only conserved for elastic. So when we say it's conserved, we mean that kinetic energy before the collision has to equal kinetic energy after the collision. Okay, and we're going to look at our kinetic energy equations for two objects before and after. Okay, so this one right here below should be the one that we write down and we'll use. Okay, so this is kinetic energy of the first object before, kinetic energy of the second object before the collision, kinetic energy of the first object after, and kinetic energy of the second object after. Okay, remember this little apostrophe symbol is the prime. That means it's after the collision or post-collision. Okay, so this is an equation that you should have in your notes and be ready to use. So now these are two equations that we're going to be able to use to find the speeds of both of these objects post-collision. Okay, thus far, the momentum that we've looked at before has only allowed us to look at the velocity of one object afterward if we've been given three of the others. Okay, so these two equations allow us to find the velocity after the collision of each object, and these two are independent of the other. Okay, so we don't care about V2 prime when we're trying to solve for V1 prime. Okay, we couldn't have done that with our last equation. These two are manipulations of that. These two aren't found in your book. Your book, I think, does not a great job of teaching how to do this step in our process. So I kind of went away from the book a little bit. I don't think it does a very good job explaining it. So these are two equations that give us an easy route to solving for these velocities post-collision. Okay. I'm going to give you just a couple minutes to get this written down. This is a pretty lengthy problem. It looks like it's not going to take that long. We're just going to use those two equations we just found, just written down. But I'll give you a couple seconds to write this problem down before we start working, because I'll have to give myself a new page. All right, so let's try this one. The mass of our first object is equal to 0.8. The velocity of our first object is equal to 2. Okay, so let's first and foremost establish a coordinate system. Okay, we normally think of to the right as being positive, to the left as being negative. Okay, so this first object is moving to the right or to the left? Left, which means our velocity would be -2. Okay, the mass of our second object equals 0.9, and the velocity of our second object is going to the right at 3 meters per second, so it's going to be a +3. All right, let's solve first for v sub 1 prime. Do I need to copy the equation up there, or do you guys all have it in your notes? We're good? Okay, so let's go ahead and start plugging things in. To solve for v sub 1 prime, we're going to take 0.8 minus 0.9 times v sub 1, so -2. We're going to add that to 2 times 0.9 times 3, and all that's going to be over m1 plus m2. Brandon, what'd you get?
Yeah, 3.29.
Good. 3.3, and our units will be meters per second. So since this is positive, that tells us it's going in which direction? To the right. Okay, we don't have to write to the right, but since we gave a coordinate system that's clear and defined up at the top, we know that a positive velocity must mean that it's going in the rightward direction. Okay, so now let's go ahead and look at v sub 2 prime. Last year. All right, so to solve for v sub 2 prime, we're going to take m sub 2 minus m sub 1. All right, so what do we get for v sub 2 prime? Negative what?
1.17. I'm sorry, 1.71.
There we go. Negative 1.71 meters per second. So that means it's going in which direction? Left. Okay, so this one would be going to the right. This one would be going to the left. What'd you say? Yep, those are our two answers. Okay, go ahead and try this one on your own and we'll see if we match.